We have been using Peirce law in the lab, and we know that it has wide application in chemical analysis. So, for a compound to be analyzed by Peirce law using the spectrophotometer, it must absorb light. This is the first thing, and the wavelengths of absorbance of light must be only due to the colored complex we made or the compound we are measuring its absorbance. And this should not, there should be no interference with any substance in our analytical solution. So any interference must be masked first. This is called selectivity. We talked about selectivity in the last lecture, and we said selectivity is the ability of the analytical method to distinguish the analyte from any other substance. So let's have some examples to see the application, the wider application of Peirce law, and how can we answer questions related to the use of Peirce law. So if you have a solution prepared by dissolving 25.8 milligram of benzene that has a molecular mass of 78.11 in hexane, and we said that pure hexane has negligible ultraviolet absorbance above the wavelengths of 256 nanometer. So we made this solution into 250 ml, and we measured the absorbance at 256 nanometer. The absorbance that we got was 0.266. This was in 1 centimeter cell, so the path length here was 1 centimeter. We need to find the molar absorptivity of benzene at this wavelength. First of all, we know that the Peirce law says that A, which is the absorbance, equals the molar extension coefficient times the path length times the concentration. We have the absorbance here, which is 0.266, and we have the path length, which is 1 centimeter, and we need to find the concentration in order to be able to calculate the molar extension coefficient. We know that we dissolve 25.8 milligram of benzene in 250 ml solution. So to find the concentration, first we need to calculate the concentration of benzene. And we are talking about concentration, we're talking about the molar concentration. So the molar concentration of benzene will equal the mass, which is 25.8 milligram, and we need to convert that into grams because we are calculating the molar concentration. So this is equal 0.0258 gram. And if we divide this by the molar mass, which equals 78.11, that will give us how many moles are there uh, of benzene in the 250 ml. But now, because we want to calculate the molar concentration, so how many moles per liter, so we divide this by the how many liters are there, which is 0.250. We will find that the molar concentration of benzene is 1.32 times 10 to the power minus 3 molar. So this is the molar concentration. So this is the first thing we need to find, which is the molar concentration. Now we know what is the absorbance, we know the path length, we know the concentration, so we can calculate the molar extension coefficient. So the molar extension coefficient will equal A over PBC. So this will equal 0.266 divided by 1 times 1.32 times 10 to the power minus 3. The molar extension coefficient equals 201.3 molar minus 1 centimeter minus 1. This is the molar extension coefficient, and this is specific for benzene in hexane at wavelengths 256. So this is the molar absorptivity or the molar extension coefficient. So the second part of the question says if a sample of hexane contaminated with benzene has an absorbance of 0.070 at 256 nanometer. This time the cuvette was 5 centimeter wide, or the bus length was 5 centimeter. We need to find the concentration of benzene in milligram per liter. So when you find a question like that, you need to be careful because the question here is asking you about the concentration in milligram per liter, not the molar concentration. So if you answer the question and you get the molar concentration as how many moles per liter or molar, and you didn't convert that into milligram per liter, you are not getting the full mark on in your question. You're only getting part of the mark. So again, using the Beer's law, we know that the concentration will equal the absorbance over the molar absorptivity or molar extension coefficient uh, divided by the molar extension coefficient times the times the path length. The absorbance is 0.070, and the molar extension coefficient, we found it here from the previous part of the question, which equals 201.3, and the path length here is 5. So you find that the concentration is 6.95 times 10 to the power minus 5, and this is the molar concentration, or how many moles per liter. Now I want to convert this into milligram per liter. So to convert it from the molar to concentration into milligram per liter, or what I need to do is to multiply this value as moles per liter times how many milligram per mole, or by the molecular mass, and multiply this by 1000 to convert it from grams into milligrams. So if I multiply 6.95 times 10 to the power minus 5 by the molecular mass, which is 78.11, and then multiply this again by 10 to the power 3 to convert it from gram into milligram, I will find that the concentration is 5.4 milligram per liter. So remember, because we are asking about the concentration in milligrams, so I have to multiply my answer by 10 to the power 3, or multiply it by 1000 to convert it from gram to milligram. Because if you multiply the molar concentration times the molecular mass, you will get it as how many grams per liter. But I want it as milligrams, so I multiplied it by 10 to the power 3, or by 1000. Another example, which is more practical example, dealing with biological samples. So if I want to calculate the or determine the serum iron concentration, we can do this in 3 steps. Uh, First thing I need to think about is what type of colored complex I need to form for the iron, because the iron in itself is not colorful. It's not colored. So I need to convert the iron into a colored complex. So the complex we are going to use here is the complex between the iron and ferrozene. So iron will make a complex with ferrozene, which has a purple color, and it can be measured at 562 nanometer. The wavelength of maximum absorbance is 562 nanometer. So first of all, we know that the iron in the serum is complexed with has a complex with transferrin. So I need to remove the transferrin, and I need to remove all the proteins and only get a clear solution that has the iron I wanted to make the complex. The iron in the blood is in the oxidized form as ferric. So the first thing I need to do is to reduce it into ferrous, because actually ferrous is the ion that makes the complex, not the ferric. So the first thing I need to do is to reduce the iron in the transferrin from the ferric state into the ferrous state. And then I need to precipitate the proteins to get rid of all the proteins from the serum. So to only, in this case, I will only separate the iron as a supernatant. So we will add trichloroacetic acid, and trichloroacetic acid will precipitate the protein, and that will leave the ferrous in solution. To get rid of the protein and only have the solution, we will centrifuge this, so the protein will precipitate and we will have a supernatant that will have the ferrous. We will take a certain volume from the supernatant, and we will react this with the ferrozine in order to make the colored complex. And the colored complex will be measured, the absorbance will be measured at the lambda max of that complex, which is 562 nanometer. Um, Also, because we have been talking about the selectivity, we need to make sure that this complex this method is selective for iron. But the serum also contains copper, and copper can make complex with ferrozine, and this complex will be colored complex as well, and it can interfere with our absorbance. In this case, we need to get rid of the copper, and to mask this copper or get rid of this copper or eliminate this type of interference, we will add a neocuproin or thiourea. So neocuproin or thiourea will make a very strong complex with copper, but not with iron in this case, and this complex will prevent the copper from interacting with the ferrozine. And now we need to measure the lambda max, which we have said before that it was 562 nanometer. So as we did in the lab, we measure the absorbance at different wavelengths until we get the wavelengths of maximum absorbance. So the wavelengths of maximum absorbance, the lambda max here, is 562 nanometer. These are the steps exactly how we do this, and I will leave that to you to read by yourself. In order to measure the concentration of the serum, we need first to establish a calibration curve. And to do the calibration curve, we need a standard solution of iron. So we're going to take a standard solution of iron and we will measure the absorbance of that iron in complex with the ferrozine at the lambda max, and then we will create the calibration curve. So we measured the absorbance of various concentrations of iron, starting from 2 till 9 microgram. So we made 1 mil of a standard solution containing from 2 to 9 microgram of iron in place of the serum. So instead of using the serum, and we created the calibration curve. Now we measure the absorbance of our sample solution, which has the iron from the serum. And then we need to find the absorbance of the unknown, and then as we see from the calibration curve, we can find the concentration of the iron contained in our unknown. Then depending on the dilutions, we need to do our calculation to find what is the original concentration of the iron in the serum. So when we are talking about preparing a standard solution, as you did in the lab as well, so you are provided with a certain solution as a stock solution, usually prepared in a certain way by dissolving a certain amount of our analyte, our standard in a certain volume. So if we prepared in order to create this calibration curve, we prepared our stock solution of iron by dissolving 1.086 gram of pure clean iron wire in 40 ml of 12 molar HCl. And then we diluted this to 1 liter with water. So this is our stock solution. And the stock solution concentration now is 1.0086 gram iron per liter, or if you want to change this into milligram, it will be 1.086 milligram iron per milliliter, or 1068 microgram iron per mil. So this is the concentration of the stock solution, as how many micrograms are there per mil. So now the question is, we said that the solution contains 1.0686 gram iron per liter and 0.48 molar HCl. This molarity comes from the dilution from 40 ml into 1 liter. So even the concentration of HCl or molarity of HCl has changed because of the dilution. Okay, so the question is, how can we make iron standard in 0.1 molar HCl for the calibration curve from this stock solution? As we said, we need to create the calibration curve with concentration in the range between 2 and 9 microgram per mil. So we said that the concentration in the original solution is 1086 microgram iron per mil. So we can make 2 microgram iron per mil standard by making dilution of 2 to 1000. So it's not going to be then exactly 2 microgram. It's going to be a bit more because the concentration is 1086, not exactly 1000. So when you take 2 mil from the standard solution and you dilute this into 1 liter, the concentration will be actually 2 point then 172 microgram, okay, per mil. It's not going to be to exactly 2 microgram per mil, but we will take this and we will calibrate it, or we will create the calibration curve based on the corrected concentrations as we have calculated them. And then we will transfer this. That means we will take 2 mil from our standard solution, and then we will dilute this standard into 1 liter. And now the concentration will be almost 2 microgram per mil. When we do the dilution, we will do the dilution now in 0.1 molar HCl, because we said that we need to prepare the solution in 0.1 molar HCl. We don't prepare it with water, so you have to be careful how you should prepare your sample. We usually add HCl because we need to prevent the precipitation of ferric hydroxide, so we need to add HCl. So to prepare the serial dilution, or the different concentration of the standard that will be used to create the calibration curve, we need to take certain volumes from the stock solution now. So if we took 3 ml, then if we took 3 ml from the stock solution, then the concentration of the iron per 1 mil and then dilute this into 1000 mil with 0.1 molar HCl, then the concentration will be 3.258, and you carry on. So if you take 4 mil, the concentration is 4.344, and so on. And this is how you get to the different concentration in the range between 2 and 9 microgram per mil of the standard iron. Once you have all of these and you added all the made the complex with the ferrocene, and then you measure the absorbance at the wavelengths of maximum absorbance, you then or at the lambda max, you will then create the calibration curve, and you can use this to calculate the concentration of your sample.